Hello everybody, and welcome back to another geometry lesson. Today is the first section of Unit 5. Unit 5 is all about triangles. So the reason why triangles are so important is because as a basic shape, they're going to be used a lot later to build onto other types of shapes. It makes sense that we should first start talking about the different types of triangles there are. So there are two ways to classify a triangle. Say I've got a triangle that looks something like this. Let's call this one ABC. Let's say that AC and BC are the same length as well. We could say that triangle ABC could be classified by its sides or by its angles. In general, we like to do both. So let's look at the sides. If your triangle has no congruent sides, it is called scalene. If it has two congruent sides or more, it is isosceles. And if all three sides are congruent, it is called equilateral. In our case, triangle ABC is an isosceles triangle. But that's not all. We can also classify it by its angles. Looking at the angles, if all three of them are acute, it's an acute triangle. If one of the angles is right, it becomes a right triangle. If one of the angles is above 90 degrees, it's obtuse. And if all the angles are congruent, it's equiangular. In this case, we do have this angle here that looks to be more than 90 degrees. Remember, a 90-degree angle is like a perfect corner, a perfect L shape. It's like right here. Because this one is an obtuse angle, we would say that ABC is an isosceles obtuse triangle. Let's try these three down here. Can you pause the video and try and see if you can classify these three? Try it out. How do we do? The first one is an isosceles right triangle. The second is scalene obtuse. The third one is sort of hard to tell, but it does look to be scalene acute. If you are ever in doubt about what a triangle type is, you can always use a protractor and a ruler to help you figure out exactly what it is. So in our case here, if I wanted to figure out if ABC really is acute, not a right triangle, I could use my protractor to measure that angle, and when you look at that, it's like 85 degrees. So it's barely acute. Let's flip the page. We can also classify a triangle based on the points that make up itself. Its vertices, essentially. So we see that we have three vertices to this triangle here, P, Q, and O. We're asked to classify it by its sides, and then figure out if it's a right triangle or not. Well, to figure out if it's scalene, isosceles, or equilateral, we have to figure out how long each of these sides are. There's a problem. They're diagonal. So the tip here says to use the distance formula to help us figure out exactly what the side lengths are. As a reminder, the distance formula is the square root of y2 minus y1 squared plus x2 minus x1 squared. So what we need to do is we need to use the distance formula to figure out what these side lengths are. I'll show you one of them, but then I'd like you to find the others. To find the length between P and Q, which I'm going to call d of PQ, the distance of PQ, I just need to plug in the x and y values of those points. So I'm going to say that Q is y2, so 3 minus, the y value of P is 2, so it's 3 minus 2 squared, plus, if I take a look at the x values, we have 6 and we have negative 1. We have 6 minus negative 1 squared. Well, since 3 minus 2 is 1, and 1 squared is still 1, we know it's just going to be 1. 6 minus negative 1 is 7. Squared is 49. So our distance is the square root of 50, or around 7.07. I'm going to mark that down on my graph here. Can you find the distance from the other sides, the distance from Q to O, and the distance from O to P? I'm going to give you the answers here in just a minute, but I want you to pause the video once again and try these out. Take a second, pause the video, and give it a shot. How'd you do? If we take a look at these other two sides, they end up measuring 6.71 units and 2.24 units. So, since all three sides of this triangle are different, what can we call it? We call a triangle that has three different side lengths scalene. So, we've classified it by its sides. The last thing we need to do is determine whether it is a right triangle or not. Well, I mean, it looks like it could be. This angle here looks somewhat right, but I don't know if it's exactly 90 degrees. Once again, we could use our protractor here, but instead I have a different idea. What do we know about two lines that form right angles? Well, if you have two lines that form a right angle, they have to be perpendicular to each other. And what we also know is that if two lines are perpendicular to each other, then their slopes are opposite reciprocals. So for instance, the slope of this line is 7, the slope of this line would have to be 1/7. Sorry, negative 1/7, my bad. So we have a general idea of what to do. We need to find the slopes of all three of these lines and compare them to see if any are opposite reciprocals. If they are opposite reciprocals, that means they're perpendicular and there's a right angle in between them. So we're going to find the slope of PQ together. Then on your own, you're going to find the slope of QO and the slope of OP. So for PQ, we could count out the slope, like go up 1/7. But I want to remind you, you can also use the slope formula. The slope formula is the one that goes y2 minus y1 over x2 minus x1, and that'll be m, our slope. I'm going to use the slope formula for this. So I do 3 minus 2 divided by 6 minus -1. Oops. And I get 1/7. Can you pause the video to find the slopes of the other two lines from Q to O and O to P? Pause here and check your work in a minute. Hopefully we got the following slopes. Hopefully we see that QO has a slope of 1/2, OP has a slope of -2. Since QO and OP are going to be opposite reciprocals of each other, we know that they must be perpendicular. Thus, there is a right angle between QO and OP. It is a scalene right triangle. Perfect. In a second, we're going to go back to the first page. However, I want us to take a look at this strange diagram down below. It looks like a triangle that has its sides extended out into rays. When we take a look at any polygon, the angles on the inside of the polygon are called interior angles. The interior angles of any polygon are going to all be contained within that polygon. But we also have these angles on the outside, formed by the rays that sort of come off of them, like this blue angle, or this blue angle, or this blue angle. Any angle that is a linear pair, that forms a linear pair with an interior angle, is called an exterior angle. But again, it has to make a linear pair. In other words, we know that an interior angle and its exterior angle have to add up to make 180. Let's flip back to the first page of the notes to fill in these three definitions and theorems that we have here. Now that we know the difference between an interior angle and an exterior angle, these definitions are going to make a lot more sense. So let's start with the triangle sum theorem. This is one that most of us have known for a long time now, even far before this class. What do we know about the interior measures of a triangle? Well, we know that if we have a triangle, we'll call these angles 1, 2, and 3, and we add together the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3, what do the insides of a triangle add up to? 180 degrees. So that there is the triangle sum theorem. The triangle sum theorem says the sum of a triangle's interior angles equals 180 degrees. That's just one of the most basic definitions that we know about triangles. But then down below, it says something weird. It says corollary to the triangle sum theorem. A corollary is one of those words that's like theorem or postulate or anything like that. Corollary is just another word that talks about a logical definition that we can use in a proof. The difference with a corollary is that a corollary is based off of a different theorem. So when we say the corollary to the triangle sum theorem, it means that somebody looked at the triangle sum theorem and said, well, if that's true, then this second thing must also be true, and wrote their own theorem about it. So the corollary to the triangle sum theorem is based off of the triangle sum theorem. Let's say I have the following triangle. It's got a right angle here. Based off of the triangle sum theorem, do we know anything about the measures of angle 1 and angle 2? Well, the triangle sum theorem says that all triangles should add to 180, and if we know that one of these angles is a right angle, that means we already have 90 degrees of that 180 accounted for. It means that the remaining two angles, 1 and 2, have to make up the other 90 degrees. 90 degrees comes from the right angle, the other 90 degrees comes from the two acute angles. With that, we have enough information to write a corollary. So the corollary to the triangle sum theorem is the acute angles of a right triangle are complementary, or add up to 90 degrees. Perfect. There is one more definition that I want to talk about, and you notice that I skipped over it for a moment. Because this definition is going to be a bit more challenging than the others. So let me draw this. Let me draw a large triangle with an extra side off of it that turns into a ray. I'm going to call the measure of this exterior angle, because it's on the outside, 120 degrees. Well, if that's true, what information do we know about angle 1? Well, if this angle is 120 degrees, and angle 1 forms a linear pair with it, we would know that angle 1 is supposed to be 60 degrees, right? So the measure of angle 1 equals 60. That's nothing new. But if we know that angle 1 is 60 degrees, is there anything that we could tell about the sum of the other two angles? We may not know exactly what measure angle 2 and 3 are, but we can still find some important information here. If angle 1 is 60, and all triangles add up to 180, it means that angles 2 and 3 also have to add up to 120, which is the same thing that was the exterior angle. We don't know what the measures of 2 and 3 are, but we do know that they add together to equal that 120. This is the exterior angle theorem. Basically, if you know what the measure of an exterior angle is, you know what the sum of the non-adjacent interior angles should be. In more exact words, more precise language, the exterior angle theorem says this. The measure of an exterior angle of a triangle equals the sum of the two non-adjacent interior angles. The measure of an exterior angle of a triangle equals the sum of the two non-adjacent interior angles. It kind of sounds like word salad, but it makes more sense when we're presented with a problem where this actually comes into play. Let's take a look at the examples in exercise 3. Here, we are asked to find the measure of a given angle, and I want to take a look specifically at E. E has us finding the measure of angle 2, this exterior angle right here. All we know is that these two angles are 75 and 64. But, according to the exterior angle theorem, the measure of angle 2 is going to be equal to whatever 75 plus 64 is. That's 139. The measure of angle 2 is 139 degrees. This even works in exercises like A, where you have the measure of JKM, but it's a bit more complex. JKM is the angle that is marked as 2x minus 5. We also know that the two non-adjacent interior angles are x and 70, respectively. So, couldn't we say that this angle here, the one that we're trying to solve for, is equal to the two of these added together? We could say that, according to the exterior angle theorem, 2x minus 5 equals x plus 70. And we can start solving this. If we subtract x from both sides, for instance, we get x minus 5 equals 70. And if we add 5 again to both sides, we get x equals 75. Just from that piece of information, we found what x is. But we're not done. Just because we know what x is, doesn't mean we know what angle JKM is. We would need to plug in x to find that. So instead of 2x minus 5, we plug in 75 for x and solve. 2 times 75 is 150. 150 minus 5 is 145. So the measure of JKM is 145 degrees. What I'd like you to do is I'd like you to pause the video here and see if you can tackle these other 4 problems. It is incredible practice. Pause the video and come back when you're ready to see the answers. How'd you do? These are the answers for C, B, D, and F. If you did not get one of these, go back and see if you can redo it. You might have made a simple error. If you still can't get it, feel free to talk to me in class. I'd be happy to show you how it's done. With that said, that's the end of 5.1. It's a short lesson. Have a fantastic rest of your day, everybody.